Section 2.2 is about measures of dispersion, and we're going to introduce the idea of variance and standard deviation. I would say in general, the variance and standard deviation formulas are the hardest thing that's going to occur on the first test. They're going to be very useful and tools that we use in the remainder of the class, but I would say this is your first taste of the type of calculation I'm going to be expecting you to do every day in this class as we get into the harder portions of the course. So it should be somewhat of a shock. This should be much harder math than we've seen thus far, but if you take it step by step, if you follow along with what I'm doing, try the classwork on your own, see where things aren't going right, I think the process is very doable. That said, I just want to warn you there is some hard math coming in this section. So where we begin is not with hard math. It's with the range, which is a somewhat easy measure of dispersion. In general, the idea of dispersion, the word just means how spread out are things. So what the range does in its most basic form is it tells us how far is the largest data point from the smallest data point. So if I had 3, 6, 11, 14, 16 as my data set, the range would take the largest data point, 16, subtract the smallest data point, 3. In this case, the range would be 16 minus 3, or 13. So again, all I need to do, if I have the ordered list, is take the number on the far right, the largest one, minus number on the far left, the smallest one. This does tell us something about the data as far as how spread out it is, but it really doesn't tell us in general how far are things from the center. That's a much more useful piece of information. So to do that, we introduce the standard deviation formula. I do not need you to know it in this math version. I'm going to present it in the math version because I want you to understand what the formula looks like and what it's saying. But I understand if this looks like Greek to you, a lot of these letters are Greek. So the first Greek letter that starts out over here is a lowercase sigma. It means standard deviation. So it's a symbol you'll be seeing in this class. It means specifically the standard deviation of a population if I have this lowercase sigma. And then on the other side of the equal sign, have under the square root sign an uppercase sigma, which means the summation of or add together each xi, meaning each individual data point that you have, minus the Greek letter mu, which stands for the population mean of a data set. So for each point, I'm going to take how far the point is away from the mean, and then I'm going to square it. I'm going to add together all those squared numbers and divide by how many data points I have. So, again, I understand if this formula looks confusing and mathy. It is confusing and mathy. Where we're going to begin is on the inside here. So we're going to start by finding a mean of a data set, the same way that we found the mean in the last lesson. Once we've found that mean and we know the average value, we're then going to say, for each data point, how far is it from that average value? You might ask, why do we have to square it? Well, the reason we have to square it is, if all we did was say how far is each data point from the mean, the ones that were above the mean would give us positive numbers, the ones that were below the mean would give us negative numbers. And by definition, those positive and negative numbers would have to balance out. So every single time, if all we did was this part where we took each data point minus the mean, when we added those all together, we would every single time get 0, because the ones that were below the mean would exactly balance out the ones that were above the mean. That's the whole idea of the mean calculation. So what somebody realized was, hey, if we don't look at this as distance below, distance above, but just instead how far it is away, distance from, we want all of these distances to be positive. The way to make them all positive is by squaring the result. So where this squared comes from is the idea that if I square a negative number, I get a positive number. If I square a positive number, I get a positive number. So if I square each of these distances from the mean that each data point is, I'll have positive numbers that I can add together and figure out, if I add them all together, divide by how many data points there are, and then square root in the end, it will get me back to what I really want to know, which is on average how far is each data point from the mean. So really, This squared makes everything positive. This square root makes everything back into unsquared terms so that it relates directly to your data set. Before we take the square root, if you didn't have it in the equation and all you did was summate all the squared distances divided by n, that would be finding what's called the variance. The variance is often reported and is useful. You'll hear it in higher level analytics. It's definitely something that's important on its own. But the larger concept here is what we're looking for is, on average, how far is a point away from the mean. To do that, we square everything to make it positive, and then square root to put it back into those terms. So this is everything being done to a data set. I understand that this is a lot to take in. I highly recommend that you try the classwork on your own, see what step you get stuck on, and then watch the classwork video going over those same problems. Really, I designed this lecture to be somewhat quick, showing you one full example, where the best way for you to learn it is then to do the next few examples on your own, get used to the process, see where it's breaking down. That said, we're starting with that data set we saw earlier that we found the range of, specifically 3, 6, 11, 14, 16. The first thing I have to do to a data set when I'm trying to find the standard deviation and variance is I need to find the mean of the data set. So the same formula we had last lecture, we add all the numbers together, divide by the number of data points. In this case, all the numbers added together equal to 50. When I divide that by the number of data points 5, I get 10 as the mean of my data set. This is just one part of the larger calculation. Once we have the mean, we now need to find the distance from each data point to the mean. So from 3 to the mean of 10, or 3 minus 10, I get a distance of negative 7. From 6 to 10, or 6 minus 10, I get negative 4. 11 minus 10 gives me a positive 1. 14 minus 10 gives me a positive 4. 16 minus 10 gives me a positive 6. So this column of numbers is just found by taking each data point minus the mean that we found. Again, if I were to add these all together, minus 7 and minus 4 would combine to negative 11. Plus 1 would get me to negative 10. Plus 4 would get me to negative 6. Plus 6 would get me to exactly 0. If I found the mean the proper way, those will always add to exactly 0. Since that's not really useful, just finding out that it's always 0, that's why we're doing this step of squaring everything. That way we get all positive numbers that when combined will give me a sense of, on average, how far is a data point from the mean. So the negative 7 when squared becomes 49. Negative 4 becomes 16. 1 squared is 1. 4 squared is 16. 6 squared is 36. All of these numbers should always be positive. If you get a negative number after squaring, you entered something wrong in your calculator. Specifically, if you put in just negative sign 7 and then the squared button, it's going to tell you negative 49 because it doesn't realize the negative is also being squared. If you want to put this in your calculator and square it once, put it in parentheses, negative 7, and then the squared button. Or just know that all the answers need to be positive. Once I have these 5 answers, the next step is that outer summation symbol that tells me add them all together. So I do that. 49 plus 16 plus 1 plus 16 plus 36 gets me to 118. 118 is the sum of all the squared distances. If I then divide that by the number of data points, specifically 5, that gets me to the population variance, 23.6. If I stopped here, it would represent the population variance, or lowercase sigma squared. So again, the variance is useful, but for the most part, this lesson is going to ask you to go one step further and find the standard deviation. One step further just means taking the square root. So the square root of 23.6 gives me 4.86. As far as my rounding conventions here, I like to go 1 decimal more than where I started. So what I mean by that, the data set is all whole numbers. When I go to find the mean, I get to 10, I would have gone to 10 point and 1 decimal. Down here, when I add everything and get the average, I'm going to 1 decimal to get to 23.6. When I then take the square root I'm going to one more decimal than what my last entry was. So if I start with something that goes to one decimal place, when I perform an operation on it, I'm going to go to one more is the general idea here. So normally I go to one decimal place in the mean, 2 decimal places in the standard deviation. That said, Cengage will absolutely tell you how many decimal places it wants in questions. If it doesn't, it means for you to include as many as possible. So, we found after taking the square root that it had a standard deviation of 4.86. What that means is this original data set has an average of 10, and on average, a data point within that data set is about 4.86 units away from that mean. There's a slight difference when we talk about having the whole population versus only having a sample. So the whole population means everybody we could have wanted to study. If we were looking at something like the ages that presidents died, and we looked at all 38 presidents who have died, that would be an entire population. We could find what the average age of death was, we could find what the standard deviation is, all using that formula we just had. If instead we wanted to find what the average age of an American to die is, there we'd probably want to take a sample of like 50 people to extrapolate and think about what's going on in the hundreds of millions of people in America. So that's a case where we'd want to use the sample formula instead with the data that we have. You only use the formula we just used when you have every data point possible, when it's told you it's a population. When you have a smaller part of the larger population, you use this formula instead. The good news is they're nearly identical. Starting at the inside, you do everything the same. You take each data point minus the mean, you square all the results, and you add them all together. So all the hard parts that we did at the start, all the same, can use the same exact steps. Where it changes slightly is right here. When I go to divide and find the variance of a sample, instead of dividing by n capital, the total number of data points, we divide by n lowercase minus 1, the size of the sample minus 1. What this really does is it makes, since we're dividing by a smaller number, it makes things slightly larger to account for the idea that in sampling there may have been some errors. If we were looking at the average age of death of somebody in America, randomly selecting 50 people, we could have just happened to have gotten a sample that skewed slightly old or slightly young compared to the true population. Because there's more ability for it to vary from the population, this calculation makes the numbers slightly larger. So again, the only difference in the process is after you do the whole top, when you go to divide, you're subtracting 1 from n before you divide. That's doing the sample variance and sample standard deviation calculation, as opposed to if you divide by just the total number of data points, then you're doing the population version. Symbols also change slightly. When we talk about a sample, we use the symbol S for standard deviation and S squared for variance. When we talk about a sample, we use X with a line over it, or X bar for the mean. Remembering back to what it was for population. For a population, we use lowercase sigma for the standard deviation, or sigma squared for the variance, and we use mu, the Greek letter, for the mean. So you can see that it's literally the same exact page with all the same info to what I did before when I was calculating this data set as if it was a population. The only thing that's changed, so still mean exactly the same, distances to the mean exactly the same, squared distances to the mean exactly the same, added up total of the squared distances to the mean exactly the same. So all these steps up to here, nothing has changed based on changing the formula. Where it changes is now, instead of dividing by 5, or the total number of data points, like we did in a population, since we're doing a sample, we want to divide by the data points minus 1. In this case, since we have 5 data points, 5 minus 1 gives me 4, so I'm going to divide 118 by 4. Notice how much larger that makes this variance. I used to get 23.6, now I get 29.5. That discrepancy will be larger when you have less data points. As you get a larger and larger sample, it will become closer, the calculation for population versus the calculation for sample. So if I stopped here, this would be my sample variance, or S squared. To find the sample standard deviation, I do the same last step. I take the square root, and that gets me to an answer of 5.43. Mean of our data set is 10. On average, data points are about 5.43 units away from that mean. Again, we get a slightly larger number this time, because when we're dealing with a sample, we have to allow for more variation. Comparing the range to the standard deviation is a step that they like you to do in Cengage. It's a little confusing the first time people see it, so I just include it in the presentation. Basically, using our sample standard deviation that we just found and the range that we found on the second slide of the presentation, we can compare the two by saying how many ranges, or the range is approximately how many standard deviations, by taking the range and dividing it by the standard deviation. If I take 13 and divide it by 5.43, that's how I answer this question. So when I do it, 13 divided by 5.43 gives me an answer of 2.394. Rounding to one decimal place, because I believe that's what the instructions are in Cengage, I would call this 2.4. So there are approximately 2.4 standard deviations within the range. Again, as long as I did all the hard calculations before, this should be an easy step. Take your answer for standard deviation, take your answer for range divided by standard deviation, and then round to however many decimal